1 second here. I always forget to turn on this thing. Everybody is logged in, right? It's okay. That was fast. Cool. Okay. So the big thing with the SIDS and stars is just understanding kind of what they are and why we use them. And the nice thing about them is that if you think about like the air traffic control environment and like how much they talk to have to talk back and forth to all the different airplanes. So the idea behind the whole thing with SIDS and stars is that it just helps eliminate a lot of communication that would otherwise be constantly having to go back and forth. As you can imagine, as planes get closer to the airport, they start to compact and they all start to get closer together. You know, they're all kind of converging in, and the closer they get, the busier it gets. It's kind of how it works. So when you're at altitude and you're flying into an airport and you're getting ready to descend in, ATC will tell you, okay, you know, SkyWest 54, 54, you are cleared to descend via the, just whatever star. Like, let's say we're going to Salt Lake. They'll call it like they have like the Brigham City 4 arrival star. So they'll say something like, you are cleared to descend via the Brigham City 4 arrival. And so what that means is that the pilot pulls out their, well, they should already have them pulled out, but they're nice electronic flight bags. They're Surface Pro 3s or whatever we're using in there now. And up on their little tablet, they bring up the picture of the Brigham City arrival star route. And as they look at that, if you look at the initial point, and I'll just bring it up just to kind of, just for our reference here. So I just want to kind of just go over SIDS and like just kind of show you kind of visually on this here. Okay, can everybody see this good here? This is the top part of it. But this is the Brigham City 3 arrival, since that's the one that I chose to pick on. This is going into Salt Lake City. I'm going to zoom out a little bit here. So, does everybody know where Brigham City is? North of Salt Lake, north of Ogden. Anyway, so this is for aircraft that are approaching Salt Lake City from the north or the northeast, or in even some cases to the northwest. Anybody really kind of coming in from the north. There's several different star routes. There's probably 4 or 5 star routes for the north. There's 4 or 5 star routes for the south, and then there's like 2 or 3 for both the east and the west. So just to give you an idea, there's a whole bunch of them, right? Depending on what direction you're flying in from, there's a bunch of different stars. And the same thing goes with the SIDS. But anyway, if you, let's say that you're flying, you know, from, oh geez, let's see. Let's say you're going Rapid City, South Dakota, into Salt Lake. A good flight from, you know, the northeast, basically. So as you're coming in, ATC, they will you've got your regular route, and we'll look at regular routes once we start getting into the flight planning stuff a lot more. But just to kind of show you like what it is here, like if you can see, thank you. If you can see these all of these different points here, like this one right here. So all of these round circles, these are all VORs, okay? So this one here is the Du Bois VOR. Over here is Jackson, so obviously that's Jackson Hole. You've got Big Piney over here. You've got Rock Springs VOR over here. Basically, all of these points, these are what are called transition points. And so as an aircraft is flying in, depending on which one of these they're approaching, like, you know, if a plane is coming from Chicago, as an example, to Salt Lake, they usually will come in over Rock Springs. If a plane, like I said, is coming in from, say, Rapid City, they'll usually come in like over Big Piney or the Jackson VOR. Obviously, Jackson Hole flights come in over the Jackson VOR. Most of the stuff from Montana, you know, goes over the Du Bois up there. Anyway, so as they're approaching Salt Lake, ATC will route them to one of these transition points. And once they get to that transition point, ATC will then say, okay, SkyWest 5454, you are cleared to descend via the Brigham City 3 arrival. You know, or it'll say you're cleared to Jackson and then cleared to descend via the Brigham City 3 arrival. So at that point, what that's telling the pilot is that once they get to Jackson, the transition point, they now need to follow whatever it says on the chart. So as we start looking at these, and now I'll zoom back in. Okay, so as they cross the Jackson VOR, they then start following this route right here. So these arrows kind of point the way that it's supposed to go. They're supposed to follow this line. So what they do here is, so from here, from Jackson, they go to this intersection right here. And you guys remember what an intersection is, right? So they go to this intersection. That intersection is called Elko. Then from there, they go down to this next intersection, which is Lava. And you can start to kind of put together in your head where these are at if you kind of know the geography a little bit. So clearly this intersection is around Lava Hot Springs in Idaho, if anybody knows where that's at. Anyway, but as you can kind of see here, it tells them, like, once they pass Jackson, it then tells them they need to track outbound from Jackson on the 209-degree radial, okay? So that will be their heading leaving the Jackson VOR. And then this right here, see that where it says 13,100? That 13,100 is the minimum, is basically the minimum altitude that they need to maintain for that segment. So typically before they get to Jackson, ATC will have already had them descend a certain amount, and then they'll cross Jackson, and then once they cross Jackson, they get the clearance to descend via the Brigham City 3 arrival. That basically means that as they start looking at the chart, they're supposed to not only follow this track here, but they're also supposed to maintain the altitude that it says on the chart. And that basically means they're cleared to do that without ATC telling them that they can do that. So when they give them the clearance to, you are cleared to descend via the Brigham City 3 arrival, that means that you're cleared to follow every instruction on the star as it's prescribed on the star. So they don't need to call, because typically if you want to change altitude or anything like that, or if you want to turn, you normally have to talk to ATC. If you don't talk to ATC, you're supposed to maintain altitude and maintain your direction. So this is basically saying that we don't need to talk to ATC. ATC is going to assume that you're going to follow the directions on the star, and obviously the pilots are supposed to adhere to that. So because of that, it eliminates a lot of unnecessary communication. So as the planes all start getting closer, ATC doesn't need to be talking to every single plane saying, okay, you descend now to 13,100, okay, you descend down to 10,000. So all of those communications can go out the window, and it clears up a lot of airspace and time for them to be able to communicate more pertinent things. Because they're looking at these planes, okay, well, SkyWest here they're coming in on the Brigham City 3. You know, this Delta 260 is coming in on the Twin Falls arrival. You know, and from any direction, you kind of get my drift, kind of more or less what they're doing. But they are supposed to just follow the instructions, fly in, and just basically follow this route. So this is kind of doing the same thing as like you saw on the sectional charts. So it's 19 miles from Jackson to this Elko intersection. You're supposed to maintain 13,100 feet. Now, as you go from the Elko intersection to the Lava intersection, that is, you actually have to maintain 15,000. So they actually got to go up just a little bit. But do you see this little cross thing here? Okay, what that is this zig line through that. That is called a changeover point. And what a changeover point is, if you recall when we were talking about the way that they have to navigate, so when they are at the Jackson VOR, they have to tune in now from, like as they're leaving the Jackson VOR, their tuner is going to say from Jackson VOR on the 209-degree radial. Now as they're tracking this way, you know, they're tracking towards these intersections. So the way that they identify this intersection is that they know that Elko intersection is 19 miles from the Jackson VOR on that 209-degree radial. So that's when they know that they're at Elko. Now as they leave Elko and they keep going this way, they still have their tuner set to the Jackson VOR. Now the other tuner, once they crossed over Jackson, should have been changed to this Malad City VOR right here. And the reason it's this one is because this Malad City VOR is the one that helps identify the lava intersection. So they're tracking one of their tuners from Jackson VOR. The other tuner is to the Malad. Well, sorry. So let me take one step backwards. As they left the Jackson VOR, so when you see a changeover point like this that crosses over you can see them on several of these. There's one here. There's one down here. But this changeover point, what it means ultimately is that on this particular route, you can't, like when you leave the Jackson VOR, you are too far away from the Malad City VOR to actually pick it up. Okay? So even if you tune into the Malad City VOR, you're not going to be able to receive it. Now that may be due to the 130-mile restriction, or it also might be due, in this case, I'm pretty sure it has more to do with the mountains between Jackson and Malad. So you got those huge mountains, you got the Tetons up there, you've got, you know, the Wasatch Front up that area. So that's most likely why it's not receivable that far out. But as you get to this changeover point, that changeover point is basically now telling you that at that point, that is when you switch to the Malad City VOR. And that's why it's called a changeover point, because you're going to change over from the Jackson to the Malad City VOR. That's where it first becomes, within the reception point of the plane. So, and the way you know where it's at is it'll tell you that you're 51 miles from the Jackson VOR, and once you tune into Malad City, it should show you as 63 miles to Malad. So that's what that means there. It's your changeover point. So then you keep going, and then you'll know you'd be able to identify the lava intersection because it is going to be 40 miles to the Malad City VOR, and it should be in total, it should be, let's see, 50, so it should be 55 miles total from Jackson. So anyway, that's how you identify that. Then you turn and you follow down, and you actually then go over the Brigham City VOR right here. And now you're descending back. Now you're going down to 14,000. And as you pass over Brigham City, you still are maintaining 14,000 in this area. Now these altitudes, just so you guys know, are MSL. Okay, these are mean sea level. So once you take into consideration the elevation of the Salt Lake area, so the Salt Lake airport's like 4,300 feet above sea level. So really, in this area, you're closer to about 10,000 feet AGL. So they're maintaining 14,000, and then they come to the Carter intersection right here, and then depending on which direction the airport is landing, whether they're landing from the north or from the south, at that point ATC will either have you go directly south on, to basically intercept. So do you remember what this feather is? You see the feather there, Ashley?
Yeah.
Okay, so that feather is just, once again, that's just denoting that the glide slope, the instrument approach for the northern runways does begin right there. So as you pass over this Carter intersection, if you are landing, depending on which way the wind is blowing, if you're going to land on like runway 16 left or 16 right or 17, landing to the south essentially, then ATC will turn you right here, and then they'll put you on this. They'll have you turn to 170 degrees and descend to 12,000. As you get to 12,000 feet, it says right here, landing south, you'll intercept the India Mike Oscar Yankee localizer, and then you'll proceed inbound and expect the ILS DME runway 16 left approach. Now, if we are landing to the north, then I know you guys have all seen it, like on any given day, like you might fly up to Salt Lake, and if you're lucky, flying from St. George, you land on 3-4 left or right, makes it a little quicker, but sometimes if the wind's going the other way, you pass the airport, and then you turn and you come back down. And just is based on the wind. That's all that is. But depending on those two different things, this arrival route still works regardless of which way you're landing. The only difference is when you're at the Carter intersection. If you are landing south, they'll turn you right then, and they'll descend you to 12,000. You'll pick up the ILS approach, and then you'll descend in via the ILS approach and land. Now, if you're landing to the north, they'll keep you going. They're still going to descend you down to 12,000, but they're going to keep you going to the Ogden VOR, and then they're going to wrap you around, and they're going to have you keep following the the star, all the way around the back end here to the Diane intersection here, and then then you turn to 155, and so now you can see after the Diane intersection you descend down to 8,000, or sorry, between Ogden and the Diane intersection you descend down to 8,000. So now if you think about it, at this point you're only 4,000 feet AGL. So then you turn this way, and then once you get to this point here, kind of where that has these dots. At this point, ATC takes back over. Okay, so once you're right here, ATC is basically going to tell you. In most cases, they're just going to have you just continue straight. But like it says here, if you're landing north, vectors for ILS, DME, or visual runway 34 left approach. So they're basically just telling you that you will receive vectors. So if you ever see the word vectors, that just means it's something the ATC is going to give you. It's just they're going to give you the instructions. They're going to say, okay, maintain 155 degrees at 8,000, and then they'll just usually say something like expect they'll call it like expect a base turn in 2 minutes or something like that. They'll usually give you some sort of a time element, like you're just going to keep flying straight until I tell you. And then when they're ready for you to turn, and when I say turn base, not sure if anybody's ever seen kind of a flight pattern, how a flight pattern is supposed to work. If you take an airport with like a single runway, as you fly, the traffic pattern is what it's called. But they, as somebody is approaching the runway to land, like they're descending in, coming right at the runway, well, that's their final approach leg. Okay. If you go out to the turn that they make before they turn onto the final approach, that is called their base turn. So, and then the leg that like in this case, this path over here that goes right along the side of the airport, parallel to the airport, to where you see it out your left-hand side of the airplane, this is called your base leg. So anyway, this isn't really important, but just the only reason it's important is because you'll just hear the terms occasionally. You'll hear, oh, they're on their base leg right now. Like especially in the ATC world, like, you'll hear them say, or ATC will say it, but then you'll also, if you ever are listening to like here in St. George, there's not an air traffic control tower, but they have what's called a CTAF. And the CTAF should have been in like the little acronym definitions that you guys saw, but it stands for a Common Traffic Advisory Frequency. And what it does is it's like in a place where there's no tower, you're going to hear these terms a lot more, but it basically, everybody is responsible because it's out here, it's Class G airspace. Everybody's responsible to maintain contact with other people. So if you're flying a plane, it's your responsibility to let everybody know where you're at all times. So when you're flying the traffic pattern for St. George, and I know you guys have seen, there's tons of little private airplanes that just kind of whiz around and flight school stuff and just doing their thing, whatever, So even in a commercial aircraft like ours for SkyWest, as we fly into St. George, even the commercial airplane has to get onto the CTAF frequency, and they have to talk to everybody, because if the SkyWest flight doesn't get on there and start talking to everybody, then these little guys aren't going to know that they got a big jet coming in. So the SkyWest flights typically at about Cedar City will tune into the CTAF frequency, and they'll start announcing their position. So they'll get on there and they'll be like, you usually will announce it. You'll say St. George traffic. So trying to get anybody who's on the St. George CTAF frequency, trying to get their attention. So you'll get on there like St. George traffic. This is SkyWest 7397, 20 miles north of St. George. Then they'll say coming in on approach for runway 19. And so that's kind of how they'll announce it. So, okay, if anybody heard that's out whizzing around out here in St. George, like in a little Cessna, they're like, oh, okay, I've got a jet coming in. They're still 20 miles north. So if I'm here dinking around, I better figure out what I'm doing, or land, or do whatever I need to do, or get out somewhere else, because they're coming in. And so
it's kind of cool because Ops will end up being, we'll be around them sometimes or taking a ride in the fire truck or whatever, but we'll hear all that, and so thinking back on some of the times that I've been right by him and I've heard all this stuff, it's just kind of like, whatever.
So you guys are tuned into the CTAF frequency out there?
Yeah.
And then you have a different frequency just for ops, right?
Yeah, we've got ops frequency as well. And we can also tune into LA if we wanted to. Or whatever.
Yeah. So as the plane starts getting closer, once it gets now down to like 10 miles, the SkyWest flight will get on there again, and they'll say, St. George traffic, SkyWest 7397, now 10 miles north, approaching from the north, landing runway 19. And so sometimes then you'll hear like a little Cessna on there, like you'll hear them talking, oh, this is Cessna 172 Bravo on base leg, turning final, runway 19, And so anyway, basically the idea here is that everybody's supposed to talk to each other because there's no tower. So if nobody's talking to each other, then it'll become a problem if somebody out there is just flying around without talking to anybody and trying to land and stuff. So it would become their fault if something would happen. Now you'll notice once you start dispatching, and especially here, if you end up dispatching for SkyWest, more than once. In fact, you'll probably have the opportunity several times to end up sitting in the jump seat on St. George flights. Just by natural design of the jump seating stuff, you're going to end up in the jump seat. But you'll see like how kind of sometimes bizarre it is to like be flying in a CTAF type uncontrolled airspace environment. It actually it sometimes can be kind of a little shady, you know what I'm saying? Like a little, not that it's like way dangerous or anything, but it's definitely obviously more dangerous than flying in controlled airspace where ATC is, if you're in controlled airspace, ATC is providing the separation for everybody. They're just giving everybody instructions. And when you're in Class G, it's everybody is kind of at their own responsibility, has to say where you're at and remember to talk to people, remember to listen, and then remember to reply, So one time we were flying down the canyon, so we'd already passed Cedar City, and like I've got so many like St. George jump seat stories that like I can't even keep them straight. But
They just ask you to take it because it's always full.
Sometimes, but the thing is, the natural, like if you're doing your annual jump seating, your first leg is usually going to start in St. George or end in St. George. So just by natural design of living here, when you do your annual jump seating, usually one of your legs is going to just by default be in or out of St. George. So that's the biggest reason. But back when I taught in Salt Lake, this class in Salt Lake, I was teaching it every Tuesday. At the first, I was teaching it every Thursday. And on Thursday nights, the flights were always way worse. So I would fly up Thursday, like on like the noon flight, and then I would teach from like 3 to 9, and then I would try to run over there and always catch the 10 o'clock flight back. And so I was trying to fly up and back in, the same day every time I did it. But when I had it on Thursdays, like the flight was always packed, and it seems like I ended up in the jump seat, way often. But then I moved it to Tuesdays, and then I hardly ever sat in the jump seat, so it was usually not quite as full. But anyway, but I've got tons of St. George jump seat stories. But anyway, one time we were coming in, and we had just passed over Cedar, so we're kind of like descending now down through the canyon here, and all of a sudden, and we're going to talk about this system today, I think, but does anybody know what a TCAS is? Have anybody heard that term before, TCAS?
I've heard it.
Yeah, you've probably heard it thrown around in the OCC, I'm sure. But a TCAS is the system inside of an airplane that is it has its own little radar system, and it can see other planes, right? and then it can also see terrain and things like that. So it knows if you're about to fly into a mountain, it knows, you know, it's going to tell you like terrain, pull up, you know. It also will, depending on if there's a plane, it'll say traffic, you know, and there's a bunch of different parameters that it has to fall within. Like if the plane is within like within 1,000 feet of you and like within 1 mile of you, then it knows it's going to alert you. It's going to say traffic, because even up in the RVSM airspace, your separation is always still 1,000 feet and 1 mile at a minimum, you know, usually more than that, but always at least 1,000 feet. But the lateral separation is usually more than 1 mile. So anyway, so it knows that that's a problem. Even in the most generous type of airspace, that's a problem. So it'll alert you, and you'll all of a sudden you'll just be going, then you'll just hear the thing, it just comes on. And a lot of times if you're listening, especially if you're sitting in the first few rows of the CRJ, you'll hear a lot of those audible warnings that go off in the cockpit if you're listening. The most common one to hear is the autopilot being turned off. It just does like a beep, beep, beep. Anyway, so if you ever listen for it. But coming down the canyon, and then all of a sudden we just get this alert. It just says traffic, and it's coming from the TCAS system. TCAS stands for, I always get it backwards. It's either terrain, terrain collision. Yeah, collision. Like everyone always messes it up. It's like, because there's so many different things you can plug in there, like terrain crew alerting system, terrain collision avoidance system. Like, anyway, but I believe it is, the correct one is terrain and collision avoidance system. But whether it be terrain or traffic or anything else. What's that?
Terrain alert and collision avoidance.
Okay. So, anyway, so that system comes on and says traffic. And then you can actually see, you have a little display, a little radar map on their primary display right here. And they can see the little plane. It'll light up. And because when it says traffic, the computer knows to like highlight which one it is that they're talking about on the screen. And then you look at the screen, and this little dot starts blinking. And so at first it's not a big deal because, you know, they were far enough out. And anyway, we started looking at the altitude, and we're like at 11,000 feet or whatever. And when it first went off, that, I don't even know what type of plane it was, but it shows you whether it's climbing or descending. It'll show its altitude, and then it'll have a down arrow at the end or an up arrow, meaning that it's descending or it's climbing. So it was climbing, and it said like 9,000 feet, but with an up arrow, so meaning that, you know, climbing up the canyon essentially. And you can see the dot moving north on our screen, and you can see us moving south. So it wasn't like directly like in our path, but it was coming at an angle right towards us. And it's climbing, we're descending. So you can kind of start to see the recipe, you know, for an issue, basically. And so at first, and then, so immediately the captain gets on to the CTAF frequency, and he, you know, it re-announces his position, like St. George traffic, you know, kind of what I've been saying, the SkyWest 7397, 15 miles north, you know, on final for runway 19. Basically trying to get this guy's attention, you know, so that he'll call out as well. But clearly, whoever this guy was, he wasn't either on the frequency, or he was just not listening, or didn't have it turned up, or whatever, but he wasn't responding. So at that point, it's like, oh crap, we're going to basically just have to avoid this guy, because the problem is when you're in an airplane and you're climbing, like especially like if you're in like a Cessna or something, if you're in that airplane, you normally can't see what's above you. You're just climbing, you know. I mean, you can, to a point, you can kind of see like if it's out on an angle, but like if you're like, you know, if you're talking a couple thousand feet above you, I mean, even just to make out another plane in general, like when you're in an airplane, is pretty tough, even if it's a big plane, you know. Especially like when you're, you know, up, you know, if you're 1,000 feet or more, like separated. Like, it's really like finding like little dots, even for like the biggest types of planes. It's really difficult. Like, I always watch pilots do it, and I'm just amazed at like how like trained their eyes are of finding other traffic, because they'll get alerts from ATC and say, hey, SkyWest 7397, do you see United 555 ahead of you? And then everyone in the cockpit's just like, you know, like looking around. It's like totally clear day too. It's not like there's clouds or whatever. And it only shows them like 2.5 miles ahead at the same altitude. Okay, so we're just looking straight, and you can see them on the screen, but you can't see them. And even ones that are like passing by, like I look at them on the screen and they're at the same altitude, and I like watch for them. And like, it's like, unless you just happen to look in like the perfect spot at the perfect moment, you normally don't see them ever. And that's huge planes. And so in this case, this was obviously a smaller plane, but he wasn't either listening or responding or didn't have any idea we were coming down the canyon. So luckily for us, I mean, the problem, you kind of see the issue here with this plane that's coming in has this technology to alert you to this, but if this was another plane, another Cessna or whatever, it doesn't have this technology that's coming down the canyon, they don't have that system, you know, or anything like it. So little planes are really, really relying on this communication to like avoid other people. And so anyway, for us, we ended up having to like turn out to the right and climb a little bit to like avoid this guy coming up the canyon, and he never said a word to us. And then our thing kept going off, you know, and it gets to the point where first it says traffic, and it's just a caution message. It's not telling you to do anything, but if it gets to the point where the computer thinks that that traffic is dangerously close enough to you, the system, the TCAS system, will actually give you verbal instructions as well. So it got to the point where it actually gave us what's called a TCAS advisory message, and it basically says traffic, you know, turn right or whatever. It'll tell you right on the thing like what direction it wants you to go. So these systems are really cool. Like if you were in another plane, like let's say this other plane that was coming up the canyon, if it had TCAS as well, then the cool thing about TCAS systems is that not only do they tell your plane what to do, but they also talk to each other in other planes. So if you are around other planes that have TCAS and it senses two planes getting too close to each other, those two TCAS systems will actually communicate with each other, and they will give each crew like the corresponding, like if it tells one to turn right, it'll tell the other one to turn left. Like it coordinates with the other system, and it tells, you know, so that it's not telling you both to turn right basically, or, you know, to turn into each other. So they're really cool the way they work. Now in this case that doesn't really apply because the one that was coming up the canyon didn't obviously have such a system. But anyway, it ended up being, we had to totally avoid that guy. And I mean, I don't know how close he would have got, but he clearly would have gotten within, you know, easily within a couple 100 feet of us. And, you know, he would have seen us at that point and probably crapped his pants. But you can only imagine, you know, the environment that you're flying in. If you're not, you know, adhering to what the rules are in certain airspaces, then you can see how easily, you know, something could happen. Like a little Cessna hitting into a CRJ, but still, you know, you got 50 people on that plane. So anyway, once they, like mid-air collisions like that, yeah, I mean, they definitely have happened. I mean, it's more common with, it's definitely way more common with two planes that don't have like TCAS type systems. One of the guys, when I taught up at Salt Lake Community College, there was another class there that you had to take in, you know, as one of the prereqs for the dispatch class, but it was just called Intro to ATC. And the guy who taught that class was, or it still even is, an air traffic controller for Salt Lake Center. And so, but he taught that on the side, but he had a plane, in fact, you can even look it up, you know, like most crashes, they become pretty famous, even little ones that just between two small airplanes. It killed, I think, 3 or 4 people total, but it was like over Rock Springs, Wyoming, and it was the same exact scenario. The guy above, there was a guy above, there was like just a pilot that was cruising around Rock Springs, just kind of doing whatever. He wasn't talking to anybody. And then there was this other guy that was flying over Rock Springs, doing some sort of a, not like a cross country, but he was going somewhere else. I don't think he was even going to Rock Springs. But this guy was talking to ATC. The other guy cruising around Rock Springs was not. Now the ATC controller guy, the guy who teaches the class, he could see the guy because he's got the radar. He could see the guy that wasn't talking, and then he could obviously see the guy that he was talking to. And as this guy was flying over Rock Springs, the controller basically said, hey, just be aware that there's, traffic here around Rock Springs. They're not talking to anybody, so just be advised that there's somebody about a couple thousand feet below you, and just watch out for him because he's not on frequency, essentially. And so the other guy, he was flying straight. So it's kind of you get into the situation here, and I know you guys have seen the different types of small planes, but you see a Cessna plane. Most commonly the Cessnas will have a wing that is over, like they're over the top of the plane and they go out, and then you see some other planes that have the wings that come out from the bottom. So the plane up here, well, I can't remember what type it was. It was like a Piper or something, but the wing it was come out from the bottom of the fuselage. So with those types of planes, you can't see what's below you. And then if you're flying a Cessna, which was the one that was cruising around here, it can't see above you. So it was like the perfect combination. This guy can't see up. This guy can't see down. This guy's doing whatever he wants, not talking to anybody, and just starts ascending, up. And then this guy is just cruising along, and this guy just ends up just going right up into him. And so there was, I think, 2 people in each plane, but everyone ended up dying. So, but yeah, he talks about that all the time, and that was a situation, where the plane's TCAS system, there was no TCAS in either plane, obviously, but anyway, that was kind of a long tangent to get off and back onto this star talk here. But basically, so the final instructions they'll get as they're coming into Salt Lake here is that they will be told to expect ATC vectors, and they'll just basically say, okay, expect us to turn final or to turn base, in 2 minutes. They just keep flying, and eventually ATC says, okay, turn left heading, 090, so they start heading out this way. And then basically at that point, they'll give them the instructions that'll say, you've got, it doesn't show it on here, but you've got these feathers here that come out on this end of the runway too. And as they turn them, the ATC will then say, once you intercept the glide slope or the localizer for runway 34 left, then you can go ahead and just follow it in, descend via the localizer or glide slope. So anyway, that's kind of how stars work. And then SIDS work this exact same way, just in reverse. When a plane takes off, they are told that they are cleared to climb via there's a bunch of different SIDs, obviously, but there's like the Ensign 1 SID. There's let's see, I can show you. So all these ones that say departures. There's the Edith 4 RNAV departure, the Fairfield 8 departure, the Leeds 5 RNAV departure, the Ensign 4 RNAV departure. So you can kind of see. There's the Twin Falls 3 RNAV departure. But anyway, they just go different directions depending on where you're flying to. But you're basically told to climb via the Fairfield 8 departure route. And then you follow it out. It's exactly reverse order. You follow the departure route out to a transition point. Like, so where a star begins on a transition point, a SID ends at the transition point, just going the opposite direction. And then once you get to the transition point, you basically are picking up either a jet airway or just further ATC instruction at that point. So any questions on SIDS and stars? So we're ready to dive headfirst into aircraft systems then?
Sure.
Okay then. Let's see. Now, as far as all the navigation stuff, if you feel like there's certain things that you don't understand about it, or things that you feel like, you know, kind of went over too quickly, just know that all of the navigation stuff, all SIDS, stars, jet routes, Victor routes, all of that stuff, you're going to end up getting an absolute ton of practice, you know, when we start doing all the flight planning. So you're going to see it over and over and over again. So I'm not too worried about you guys becoming familiar with it, because it's really like it's going to become a huge part the last few weeks of class. You're going to see it over and over and over, and you'll have a lot of chance during that time too to ask a lot more navigation questions about, well, what about this and this, because you're actually going to be doing routes and designing routes, and as you design those routes, you're going to, all of this stuff with the navigation is going to come a lot more kind of, you know, into play as far as being able to see it firsthand and actually working with it. So so now we are into the Crj700 Specifications and Systems. So specification-wise, and this document will be available for you guys as well. It's already been in there in the Google Drive, but it'll also be, it's in the Crj700 folder on the Google Drive, but it also will be in the week 3, day 3 folder too. So so general, we're just going to start out with the basics. So the Crj700 has a flight crew of 2 and a cabin crew of 2. So going back to the cabin crew stuff, and this is kind of more of an ADX thing, but does everybody know the parameters for flight attendants needed in an aircraft? Yeah. 1 flight attendant per 50 passengers. So this says passengers up to 78. So this one, it's just simply because there's more than 50 that there needs a second one. So if we had 51 passengers, you would still need 2. So 50 is the limit, and then if it's over, you know, so we would need 3 as soon as we get to, we can go up to 100 with 2, and then at 101 we would need 3. And that doesn't depend on the actual number of people on the plane. It's based on the number of seats on the plane. So a lot of times you'll see a totally empty flight to, you know, some long haul international flight that has 25 people on it, but it's a plane that seats 330. Well, it's going to have a crew based on 330. So you get a lot of special attention from the flight attendants.
I guess I love
Yeah.
whole row.
So with the, so this says passengers up to 78. Now in our, in this class, we are going to use a 70-seat configuration. That's what we're going to base off everything that we do in here for our weight and balance and everything. So just, you can configure a Crj700 all the way up to 78. But that's based on having like no first class and, you know, having all the smaller seats and everything. So we are going to use a configuration of 70 in this class. It also makes it easier for numbers.
What were all the aircraft categories again? At the beginning of it.
Oh, sorry. Yeah. So as far as SkyWest aircraft categories,
the 7 and the 175 are C, and then 200 and 900
Our D. Yeah. The Brasilia, when we had it, was Bravo. Yeah. But yeah, the 700 is category C, as in Charlie. Engines. 2 engines. They're both General Electric CF34-8C5 turbofans. Each of them have 12,670 pounds of thrust at takeoff. The flat rating is 13,790 pounds of thrust at, that's basically saying the max output, and that's based on a temperature of 86 degrees Fahrenheit. And so you start seeing where these little things where you're gonna start seeing this whole ISA thing a lot more when you get into aircraft performance. But ISA plus 15 degrees Celsius is basically where it performs the best. Just kind of more of just a figure. That's not something you need to like really focus on though. Avionics, Collins ProLine 462, EFIS, ICAS, dual altitude heading reference systems, traffic alert and collision avoidance system, TCAS, Collins digital weather radar. We'll talk about all of these individually. So right now it's just kind of going over the basics. Dimensions, external, the length overall 106 feet 8 inches. Wingspan 76 feet 3 inches. Wing area 760 feet squared. The height overall is 24 feet 10 inches. Fuselage diameter is 8 feet 10 inches. And turning circle radius of 75 feet. These next things are just talking about the door, all the different doors on the plane and how high they are off the ground. Don't really need to pay too much attention to the height, but there's, I believe, 9 doors. 1, 2, 3, 4. Oh, it doesn't have the other one. Anyway, it has 9 doors overall. They're not all listed here. These are all doors that are going to be the larger type doors. What's that?
Are they including all the loud water, air starter?
Yeah. Well, yeah, usually. And we'll look at doors more specifically here in just a minute. These weights. These weights here are going to be something that you want to memorize. Obviously they're here. You'll have access to this sheet, so you can refer back to the sheet whenever. But memorizing an aircraft weights becomes a very important part of aircraft performance. So Crj700 max ramp weight is 75,250 pounds. So the max ramp weight, what that basically means is just when it's sitting, at the gate, essentially, you can never load it up to weighing more than 75,250 pounds. You'll end up getting a restriction. Now you can, it's not necessarily easy to reach that figure, but it is reachable. Like, depending on how many people and bags and how much fuel you have on board, you can easily reach the max ramp weight. Now you look down, the next one, the max takeoff weight is 75,000 pounds. And that's going to be a big one to remember. Takeoff weights and landing weights are the 2 biggest ones. But the max takeoff weight is 75,000 pounds. So when you compare that to that max ramp weight, 75,250, a lot of people, the first thing they ask is, well, how can you have a ramp weight higher than a takeoff weight, right? So basically, the max ramp weight is more. That's basically calculating in that you are going to burn fuel as you taxi out. So it's basically, you can't take off unless you're 75,000 pounds or lower. So that's basically, in that scenario, that means you would have to burn off 250 pounds of fuel as you taxi out. You'll notice that fuel, also with aircraft, it's all going to be in pounds. So it's not going to be in gallons. It'll always be in pounds. If you ever want to do a conversion, 6.7 pounds is usually about 1 gallon. So, but not that you ever would need gallons, because you're never going to need gallons in this class. It'll always be pounds. So 75,000 pounds at takeoff. So you either got to burn the fuel if you weigh more than that, or throw somebody off on the taxiway, whatever. The max landing weight, 67,000 pounds. Max zero fuel weight, 62,300 pounds. So zero fuel weight, that is basically the weight of the plane itself loaded up with passengers and bags, but with no fuel on board. So it does become an important figure to use when you do weight and balance. And you'll see it a lot. You're going to see all of these numbers a lot. So you'll understand why how we use all of these numbers. But zero fuel weight. So if you were to load up the plane with 70 people and 140 bags, whatever, not taking fuel into consideration at all, just the simple weight of the plane and then the passenger and the bags, you cannot exceed 62,300. So just by kind of simple math there, you can tell that if ultimately we can get all the way up to 75,000 for takeoff, that would be all fuel from 62.3 all the way up to 75,000 pounds. So the operating empty weight is 43,500 pounds. That's just the weight of the plane itself with nobody on, no fuel, no nothing. So the operating empty weight, just a little side note, is it does include the weight of the crew members and their bags, and it also includes a certain amount of what we call unusable fuel that's on a plane, and then just like the standard liquids that are in a plane, oil and different lubrication stuff, and just stuff that's already in the plane to make the components work, the hydraulic fluid, all that stuff is included in the operating empty weight. All that stuff plus the crew and their bags. So you don't ever have to add in the weight of the crew afterwards. Maximum fuel load is 19,450 pounds. Now, kind of the same thing, just by doing the simple math there, you can see that if you did have the maximum fuel on board, you would never be able to reach that zero fuel weight of 62,300. So it technically, if you're at 62,300 zero fuel weight, then you would never be able to put on the max fuel. Well, you could, but you'd be way overweight. The maximum payload, 18,800 pounds. And then if the maximum payload with the full fuel load would only be 12,300. So you can see that the payload and the fuel go into each other by about 6,500 pounds. Performance range. So So the CRJ700 series, 701 extended range, 70 passenger aircraft. The range is nautical miles 1,732, statute miles 1,993, and 3209 in kilometers. The speeds that it can go. The highest cruise speed setting is Mach 0.825, which translates into 473 knots per hour, 544 miles per hour. Normal cruise speed, though, is planned at 0.78. Does everybody know what Mach is? Or heard the term Mach?
Something to do with the speed of sound, isn't it?
Yeah. So Mach, like when this gives you this Mach number, so if you're Mach 0.78, so if you were to consider Mach 1 is the speed of sound. That's what that would be breaking the sound barrier at Mach 1.0. So we're basically going Mach, we can go up to Mach 0.825, Mach 0.70. So pretty much if we're normal cruise speed, Mach 0.78, we're pretty much going 3/4 the speed of sound. So that's all that is kind of talking about there. So let's see, the FAR takeoff field length, sea level at ISA is what that is in the parenthesis there, is what it's meaning. So sea level at ISA, maximum takeoff weight, it needs 5,500 feet of runway. And for landing, the field length at sea level, the max landing weight, it would need 5,090 feet of runway in order to stop. So when we get into performance a little bit more, you'll see how these things change quite dramatically. So this is just giving us a generic number to go off of, but it's based off of sea level and ISA temperature, basically. So, but as we already discussed when talking about ISA, temperature conditions, regardless of where you're at, whether you're here or whether you're on the coast, conditions are rarely just ISA. I mean, occasionally you'll come across something like, wow, we're at ISA here, like exactly, like it's perfect, But normally we're never at ISA. It's always going to be colder, warmer, the elevation will be higher, you're not right at sea level. There's all of those things will normally change. When we get into performance, you're going to see how those really do change. As you start to get into a higher elevation airport with a really hot temperature, you'll see that required field length to take off in some cases can jump all the way up to 9,000 feet. An extra runway, doubling the length that you would normally need at standard ISA temperatures and sea level. So, but this is just giving us that generic thing to go off of. Fuel consumption per hour, at the average cruise speed, it burns 440 US gallons. So that's probably the only place in here you're going to see gallons ever. So if you times that by 6.7, you should be able to get your pounds. Maximum operating altitude, 41,000 feet. And that's just based off of the manufacturer.
Do the 2 and 900 vary from that very much, or are they pretty close?
Like as far as all those categories?
Yeah. I like the max weight and stuff like that.
So like as a comparison to like the 900, the 900, it can hold more payload. So basically, when you look at the 900, the only thing, the 900 is just an extended version of the 700. It has the same engines. It's the engines themselves are rated a little bit higher, but it is the exact same engine. It does have a little bit more thrust output just because they rated it higher, but it has the exact same fuel capacity. It has everything else is pretty much exactly the same as the 9 or the 700. It's just it's like they took the fuselage and just added in like basically 2 more sections of windows. So its performance can go up to the 900 can go up to a takeoff weight of 84,500. So about 10,000 more pounds basically on payload. But it has the same fuel tank capacity. So it's kind of a weird thing with the 900 is that you can't 900 like if when you were looking back at those weights and you could see if you loaded up the plane all the way up to the max 0 fuel weight, you could overfuel a 700, right? Well beyond. You could actually go 6,000-7,000 pounds beyond the max takeoff weight in fuel. In the 900, because it's the same exact fuel capacity, but it has an extra 9,500 pounds of takeoff capability on the weight, you technically cannot overfuel a 900. So, because on a 900 you can take max weight with max fuel. And anyway, it's kind of a weird dynamic. It normally never works that way with airplanes. The E175, it's just barely more than the 900. It can go. It has a tank capacity of 20,800, so like an extra 1,300 pounds or whatever. But the max takeoff weight on the E175 is 85,517 or something like that. So about 1,000 pounds more than the 900. And yeah, then the landing weights are both, they're like 75,000 pounds instead of like 67,000 on the 700. The 200 max takeoff weight is 53,000 pounds. And max landing weight is 47,000 pounds. So just in comparison, the biggest difference really is from the 2 to the 7. The 2 between any of them really, but that's where you get the real big drastic differences.
So when the fuel is over fuel in the aircraft, which we hear them do from time to time, you just have to burn it off?
They either have to defuel or burn it off, yeah. Defueling, though, takes a really long time because in order to defuel, they have to find a fuel truck that is completely empty to begin with. And then that's the only way they can defuel back into it. So, yeah.
I saw 8 cars yesterday from a guy zigzagging that he had like
which just makes me
1,300 or something extra.
Really?
Like I'm just zigzag, like I'm just zigzagging around. They got like extra 1,300. Like,
yeah, that's crazy. Yeah, overfueling happens all the time.
You can't just top them up, huh?
you just top them all.
This is just amazing to me. It burns 400 gallons an hour.
Yeah.
Wow.
Yeah. It just becomes really like, it gets to the point where, yeah, you got to get below your max takeoff weight. And the other thing, too, is you'll see this when in performance, but the max takeoff weight says 60 or 75,000 pounds, but that is also considering that all the conditions are perfect, too. So when you get into these different weather conditions and the high elevation, hot temperature stuff specifically, or if you get into runways that have contamination on them with ice, snow, standing water, all of those things will reduce your takeoff weight too. So, I mean, it's very common, or even some MELs, once we start getting into MELs after we do systems here, you'll see MELs like where we have, if like there's a system called the anti-skid system, and if that is in op on an airplane, your landing weight is really what's hurt on that. But I mean, it makes it so in some cases you have to kick off half the plane just to make it. Yeah.
Hard, wouldn't it?
That's what I work with the dispatch supervisor, and I have to find like certain cities that can't even go to.
Yeah.
I hate it.
Yeah. Anti-skids are among the probably the single worst MELs you can have, but yeah, in a lot of cases, if you don't, you also, it increases your landing distance way, it adds a lot to what you need to land. And so a lot of runways don't have, if they're short, like a lot of our airports we go to, it can't go to at all because it can't even calculate the performance because the runway, even with a completely empty plane, it can't do it.
Nashville is one of those.
Yeah, Nashville's kind of weird. Do you guys want to take a break? Before we dive into the PowerPoint? 10:30 right now. Let's just take 10, 15 minutes.
I'm going to slide really quick with the speed and everything. We try to get all of them.
Okay, you guys ready to jump back into this then?
Some like space.
Yeah, because I was like, my save and travel again.
She's a chameleon.
You're trying to
Sorry,
say
blood
blood
temperature, air temperature.
That would be enough guy. Let me see. Smirky, yeah. You can come back and join the food table. The food table. You gotta be with great people.
Oh, I didn't even realize that. It's really dark over here.
Okay, so getting back into the 700 here. The airframe type certification is referred to as a CL-600-2C10. It's made by Canada Air. Canada Air makes several different types of jets, including the 200, the 900, the 700. They also make a lot of like props and things like that. The actual origin of this particular jet came from the Canada Air made a Learjet it was called the Challenger, and you still see them a lot around, but it looks like an even really shorter 200. It looks like a little 200 with like 5 or 6 windows. Anyway, the 200 ultimately came from the Challenger Learjet, just extended it out to it, made it then a 50-seat 200, and then they took that plane and then they made that longer and bigger and made that into the 700, and then took that plane and made it longer and bigger and made the 900. So the CL on the type certification actually stands for Challenger. So the airframe is Challenger 600, which the 200, the 700, the 900 are all CL-600. And then the only thing that distinguishes between them is that those last 4, the 2C10. I don't even remember what the 200 is and the 900, but if you look them up, you'll see that they're different. But either way, that's not a major thing that you gotta pay attention to there, but just kind of more of just useless info. It was made from a collaborative effort from manufacturers in multiple countries. General Electric makes the engines, Avcorp makes the vertical and horizontal stabilizers, Manasco Aerospace makes the landing gear, Rockwell Collins makes all the avionics, and Allied Signal Aerospace makes the APU. We already kind of looked at this part. The only thing in addition here, the main passenger door seal is only 4 feet 7 inches off the ground, eliminating the need for an escape slide. So that allows the CRJ aircraft to have those air stairs that you can go up and down. The E-175 doesn't have air stairs because it's too high off the ground to have air stairs. But when it's too high off the ground to have air stairs, you also have to have those emergency slides. So I'm sure everyone has seen how that changes things, and also a lot of times becomes an issue when somebody accidentally blows the slide.
In Calgary.
Yeah, that's an awesome place to blow the
And I
slide.
found it, he's like, I'm just so glad it wasn't me, don't tell anyone I said that.
Usually it's flight attendants, it seems.
Yeah.
Maintenance does it often as well.
Residence maintenance or
Yeah.
pilots.
That's
Yeah.
why we get all the warnings.
Yeah.
I love how they have the countdown. It's been 3 days since the last flight deployment.
Yeah, they're
Yeah, they have
expensive.
it on the flight page.
They're expensive. They're like 10 or 15 grand to replace.
Every time there's an incident, they let you know, like detailing what happened. And she got full of that, and then.
Yeah, from the shift manager point of view, usually the first person, like if you send out, because we send out the slide deployment notification when it happens, and usually the first person to call is Sonia Wolford. Like, and a lot of times she finds out before we even do it. She calls us and saying, hey, I think we had a slide deployment. And I'm always like, oh, shit.
They probably call her first because they're scared.
I'm sure. Well, and the flight attendants definitely do. They usually either call their little chief flight attendant, who then calls her, or directly to Sonia. But yeah, I think that they freak out before they tell anybody. They take it right to the head honcho. Because yeah, there's been several times. If we don't know about it, then we're just assuming the aircraft's good to
Every
go.
time they do, they have to get retrained on the 175, so they have to go back to a current, if they don't get back. Yeah.
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 How do they do it? They push a button or something?
No, they have a door on,
Two
you know,
black.
and it's,
Yeah.
Oh, really?
they don't do the big
It's
red knob.
really easy to do.
Yeah.
Then do not open, and then they just lock it.
Yeah. So the CRJs are nice from the fact that they can just flip open the door and then it has those stairs on it. It also makes it so you don't necessarily need jet bridges and things like that. Nobody likes walking down the stairs, but end result is that you can if you need to. The E-175, everywhere it goes, for us, we always have to take it to airports that have jet bridges. So it becomes a little bit more problematic in the case of diversions and things like that. Anytime you divert an E-175, you got to make sure that they have a jetway, that they have, or whatever
The rolling
parameters.
stairs don't work for the 175?
They can, you can do it, but it's got to be like the perfect. A lot of people, unless they're certified on the 175, won't use the rolling stairs.
Is that why, like, when they're talking about stuff like that, they're like, they can't service it?
Yeah. Because not only does the ground personnel, they have to be trained on the 175, so they may not be able to work it if you divert there. And
Send me St. George.
yeah, so yeah, there's a lot of whole different things, but the biggest thing is really the jetway thing. So especially if you're diverting to somewhere that's like late at night. A lot of those jetways already have overnight aircraft parked on them for the night. So anyway, CRJ is nice. You can just pull up, pull the door open, people can jump out, and then they can just go, or whatever they want to do. So the pavement width required for a 180-degree turn is 75 feet. We already saw those. Aircraft general key points, noise, and exhaust levels. The Crj700 meets the most stringent FAA noise requirements. Due to the height of the tail section and the location of the APU, there is no danger area for APU exhaust. So Andrew might be able to talk more about that. Like the Crj200 has like an APU, we'll talk about the APU in a minute, but the exhausting is like right next to one of the doors. Yeah. Anyway. Equipped with one aft lavatory. The flight deck door is reinforced, can carry up to 19,594 pounds of fuel, capable of ranges, this says 1985 at Mach 7.4. Doesn't really matter though. Many systems have been improved and others automated. I hate when this thing does that. Automatic flight control system. The automatic flight control system provides integration of the flight director and autopilot systems. The auto flight control system controls and supplies information to dual independent flight directors, a 2-axis autopilot, automatic pitch trim, and 2 independent yaw dampers. So the autopilot provides command inputs to the ailerons and the elevators. Does everyone know what an aileron is? An aileron is the thing on the wings, on the very outer edges. What turns? What's that? Those are the flaps, or the spoilers in the flaps. Yeah, the aileron is basically just what turns the aircraft when you're flying left to right. But it's the very far outer edge of the wing on the back part of the wing that goes up and down. The elevator is back up on the tail, and that's what helps the plane, like, you know, it'll pitch up and down, basically, like when it's climbing, to help pitch it up or pitch down. But it's just kind of the same idea as an aileron. It's just that it's on the tail, and it just makes the plane nose up or nose down. Rudder is controlled by the yaw damper system. So the rudder, also, you know, up on the tail section, has the, should bring this back up. Let me see if I can go back up to the, here we go. So going back to the ailerons are out here on the outer edge, like right here and right here. That's what makes the plane turn left and right. The elevators are right here and right here. And those also go up and down, and that's, you know, your pitch angle. Nose up, nose down. Your rudder is going to be this section of the tail right here, and this thing will kind of turn left and right, but it's horizontally positioned. So as you're flying through the air, if you add rudder, you know, it basically will help you adjust for the wind. So if the wind is blowing you this way, but you still want to maintain this heading, then you have to put in a little bit of rudder to fly this direction. How many of you guys watched that crosswind landing video? You notice all the planes, they come in with the nose pointed like straight this way, and they're flying like this, right?
Yeah.
That's the rudder that does that. So you have so much wind pushing the nose of the plane over, and you're still trying to maintain going straight. But what they do is they leave the rudder out there like that. I mean, a lot of times, I mean, depending on the strength of the crosswind, a lot of times, you know, I mean, they're like facing this way, looking out this way, you know, like going like, you know, landing. But right before they land, they kick the rudder the opposite direction, which makes that whole nose shift over, and then they set the nose down. You saw how crazy it gets. I mean, it's kind of funny to watch those videos because you don't ever feel like it's like that in the plane. But I can, for those of you guys that fly a lot, I can promise you that almost every, not every, but I bet several of your flights have been something similar to probably what you saw. Not necessarily to the severity of what some of those were, but I mean, I've landed several times here in St. George, you know, where it's been way windy. We've had to circle around, land on runway 1, go in the other direction, and it's been like a 30-knot crosswind. I mean, and you could totally, and one time in the jump seat, you know, you could totally see how that we were pointed out. But for a pilot, that all of those that you saw that actually landed, I mean, it's fairly routine. I mean, that's fairly normal. So, and very common. Anyway, back down. When the autopilot is engaged, the auto flight control system maneuvers the aircraft while the pilot monitors the flight path by observing the flight guidance information presented on the EFIS display. EFIS stands for Electronic Flight Information. Screen.
Screen.
Yeah. Well, it's technically system, but it's, I mean, it shows up on the screen, I guess is what I mean. Electronic Flight Information System is what EFIS stands for. I don't know why this thing keeps blinking out. It automatically goes back up. It says that it's 75 or 76 in here.
No way. I think it lies. Yeah, that thing is not accurate.
Whatever. So I'll just...
Psychological thing, you see 73, get 73.
So auxiliary power unit, that is the APU. Everyone heard of an APU before?
Yeah.
What are some of the problems some of you know of just off the top of your heads that if, yeah, you need a huffer, but what is probably the most common deterrent of not having an APU? Does anybody know?
Money?
Money?
Are you saying like it costs a lot of money to run the APU?
Well, not so much, but like let's say the APU is in-op. Does anybody kind of know what the biggest problem that causes? Or has maybe just overheard the problems that it causes? Why do, like, you hear about pilots refusing an airplane because it has no APU?
They're hot.
Oh, is that what the flight attendant pulled off on one of those, like, the other day?
Typically, it's the captains or the pilots that'll refuse it. But it's because when the plane is on the ground and the engines are not running, that's mostly when you use the APU. But the APU runs the air conditioning system when the engines aren't on. So it's not so much of a problem when you're up flying and stuff because the engines will provide the air conditioning. It's just when you land and then you turn off those engines and you go up to the gate and then you don't have any APU, the plane sits there and heats up. And obviously it's a metal plane and it's a tube and turns into an oven, you know, and so it just gets way hot very fast in hot places. So that's the biggest reason that having an APU in-op is crappy. The other ones obviously is that the APU is used to start the engines as well. So if you don't have an APU working, then you have to get a huffer cart or an air start bottle to provide air to the engines in order to start them without the APU. So APU that is in the 700s, the Honeywell RE220 APU, automatic fault detection, shutdown, and in the event of an APU fire on the ground, automatic fire extinguishing protection. The primary function of the APU is to operate a, let's see, kVA, is that kilovolts? Anybody know anyway, whatever. A 40 kilovolt, I'll just say kilovolt generator. Doesn't really make any difference if we know what it is. But anyway, the primary function is to operate a generator. Just say that. Generator. And that would be an electrical generator. Secondary function is to supply bleed air for air conditioning and engine starting. Does everyone remember talking about bleed air? We talked about it a little bit when we were talking about anti-ice systems. Anyway, so the APU, if you can think about it this way, the APU is like a little mini jet engine, okay? The only difference is that it's not an engine that like, it has an air intake. I mean, it functions the exact same way a jet engine functions. It's just a really little tiny one. And we're not necessarily, we don't obviously use it for any engine power per se, but we use it because engines in general, just whether it be your car or whether it be a jet engine or whatever, engines provide electrical power. And in the case of jet engines, they suck in air and then use that air, they combust that air, and then, you know, that all creates your thrust and everything else, and your, you know, that turning of the engine creates electrical power. But then also, when we were talking about the anti-ice systems, we were talking about how a jet engine sucks in all this air, and then it, you know, spits a lot of it out the back, but then the plane itself also will take a lot of that air that's coming into the engines, and they will redirect that air. Instead of having it just go out the back, they will redirect that air, and they'll use it for other things like bleed air for anti-ice. They'll use it for, in this case, engine starting. And so the way that that works is the APU will get turned on, and it's turned on just electrically. So if the APU is functioning, then the pilots can, without having any engines or APU on, you know, once they, let's say they just walked into a plane that was sitting there overnight, it didn't have any power on the plane at all other than just the GPU hooked up to it. The GPU is just the plug that they hook in from like the jet bridge that they just plug into the nose of the plane. And that just gives electrical power, but that electrical power is coming from the ground, like it's coming from the airport, just, you know, plugging it into your airplane. So they'll use that. So the plane, the APU, in order to start, the only thing that it needs is just ground power. So as long as you plug in the GPU to the aircraft, then the pilots can get in the plane and they can fire up this APU, and the APU is located back in the tail. And when they fire up the APU, it's like you kind of hear, have any of you, when you're just boarding an airplane, it sounds like an engine is always on? You know, you always hear that low, like, whistle, you know? It just sounds, anyway, like, especially like right as you come out of the jetway, like that little space between the jetway and the door of the plane, kind of look back. Anyway, that's the APU. It's really loud. It is a jet engine, so it's loud like a jet engine. It's just a little tiny miniature jet engine is all it is. And it sits back in the tail. It's totally enclosed and encased. And they can fire it up from the cockpit, and they turn it on, and it starts to suck in air. There's this little door that opens, and it just kind of flips down, and it allows for air to come into the APU and for it to draw air in, and then it just spits the air usually out the back. In the 700, the exhaust comes out of the tail cone. On the 200, the exhaust comes out of the side of the aircraft. That's where he was saying they use it to heat up. In the 700, where it comes out is too high off the ground to like really have anybody. They moved it up so that because a lot of people would get burned and stuff. And if you were standing right next to that exhaust when it turned on, like if you didn't know that it was turning on and somebody was standing right there, they could get very badly burned, basically. So in order to avoid all of that risk, they ended up moving the APU exhaust up high up onto the tail to where nobody can get, you know, affected by it. But you also can't warm up your hands. Yeah. So anyway, as the APU starts running, it has this air, you know, that is coming off the engine, and the airplane will kind of harvest some of that bleed air that's being sucked in and then going out the exhaust. It'll take a portion of that bleed air And when you want to start the engines, jet engines start, they have to have air flowing to it in order to start circulating through it and turning the, the turbine, the fan. So in order to get that air, they redirect part of that APU bleed air, and they can hit a button, and then it just sends it to whatever engine that they're wanting to start. They can send it out to the right engine, and it'll start making the that bleed air run through that whatever engine they're wanting to start. And as the air gets in there, they can turn on their starter, and which will ignite the fuel and the air all together, and then it starts that whole process of getting the engine going. And an engine startup takes roughly about 30 to 45 seconds probably, total to get it from where you first.
How did they get that engine started?
Yeah.
Air start, really.
So without the APU, they got to get like a little. There's a couple of different ways, but most places have what's called a huffer cart, and it's this cart that they can drive out, and they park it next to the engine, or there's an outlet on the plane that is basically for external air. I don't know what do you know what it's called, that outlet? Anyway,
For the huffer?
Yeah, for the huffer. It says something. It's something there. It's like external air.
Auxiliary external air or something.
Yeah. Anyway, they basically connect this machine, and all the machine does is it's kind of like a vacuum. Like a blower instead of how you can turn a vacuum and flip it. So it's like a vacuum.
A donut ring on it that you have to push onto the plane. It's got little ball bearings in it that hold it on. And if it's not on right, when you turn the air on, full power, it'll shoot off back at you and can really hurt you. So you got to make sure it's on, and then when you go to push the air on, it's just a huge, what would you say?
It's an oversized air cannon.
Yeah.
You pressurize it, pull it out.
Extra large potato wheel.
Yeah. Anyway, so they have those machines. They hook them up to the plane, and they just start blowing air into there, and then that's the air that they can redirect that air that's coming from the machine over to the engine to start it up. And then once they get one engine started, that's all they need, because once you start one engine, you can take the bleed air from that engine and you can start the other engine. So you just have to be able to start one engine. Now, in situations that you've probably seen, like where we accidentally send a plane that has no APU or an in-op APU to a station that doesn't have an air cart, which happens more often than not. The coordinators are always supposed to call ahead to make sure if a plane is routed to 5 different airports for the day, the coordinator is supposed to call and make sure that they have a working air start before that we send a plane there. But sometimes the air starts, stop working when they get there. I mean, there's a lot of different things that happen, but if it goes to an airport that does not have an air start, and if we find out about it before it gets there, then we will have the airplane leave one of the engines on while it's on the ground. It's kind of a tough process, because in order to fuel an aircraft, you're supposed to have the engines off on the side that you're fueling. So you have to go through a lot of different procedures with fueling, with the passenger loading and unloading. You have to, when you're doing all this, sometimes you have to switch the engine that's on, from the left side to the right side, and then vice versa. You got to switch it back, and you got to shut down, redirect the air, turn on the other one, shut down that one. So it becomes, we call it a hot turn is what they call it kind of in the airport ops world. But anyway, if we don't know about the issue before it gets there and they shut down their engines, then the plane is grounded, because it doesn't have any way of turning the engines back on. They'd have to get the APU fixed, or they would have to find somebody else maybe on the airport that has an air cart, maybe the FBO or maybe another airline. But in the case where we're the only operation, we're the only flight in some of those podunk Minnesota cities, none of them have air starts, by the way, we are pretty much just dead in the water. We have to send a mechanic up to get the APU working in order to get, it turns into a road trip, basically. So the primary function, once again, is to act as an electrical generator. The secondary function is to supply bleed air for air conditioning and engine starting. So while the APU is running, that bleed air, while it's sitting there on the ground, is redirected in through the air conditioning packs, and then it helps cool down the plane. Now, have all of you noticed when a plane pushes back, how when it goes to start the engines, that the air conditioning will turn off? Everybody always wonders what that is, and you'll always notice passengers like, what the, they just go and turn off the air, like freaking out, like thinking, why would they turn off the air? Like it's freaking hot as hell, and they turn off the air. And then you always see them start to adjust the knobs. It's just, I always think it's kind of funny because they just don't understand that bleed air that was being used for the air conditioning, when you go to start the engine has to take all that bleed air. You've got to shut off the air conditioning system so that it's not drawing any of that air, and all of the air that then was coming out is being redirected to the engine so that it can start. Then you notice it starts up, and then as soon as they get them back running, then they hit the air conditioning packs buttons and turn them back on, and all is good. But for that 30, 45 seconds while they're starting the engines, everybody's freaking out. The maximum operating altitude is 41,000 feet. The maximum starting up altitude is 37,000 feet. So that's just to use the electrical part of the APU generator. So you can't, if it's not already started and you're above 37,000 feet, then you would have to go down to 37,000 in order to actually turn it on, and then you could go back up to 41,000. But if you're using the bleed air, then you've got to be 25,000 feet or below. The APU, when it's on, it burns 260 pounds of fuel per hour. So that is something that you're going to want to remember there. So regarding the APU, the things that you want to know that you might be quizzed on are just going to be, what are the primary and secondary functions of the APU? How many, and then basically how many pounds of fuel does it burn per hour when it's on? And then also just know as well, like if I were to ask you a question like, what considerations, do I need to take as a dispatcher when I have an APU that is in-op?
The primary function was an electrical generator, right?
Yeah, that's the primary thing. Primary electrical generator, secondary is supply bleed air for the air conditioning and engine starting. And it only uses that bleed air for the air conditioning when the engines are off. So once again, the APU is a primarily functioning, it's really a ground tool. It's not so much of an in-the-air tool. Typically after they start the engines, they just completely turn off the APU. They don't turn on the APU again usually until you're landing. So part of the landing checklist is to turn on the APU. So typically the only time we use the APU is just when we're on the ground. That's it, without engines on. So if you think about it that way, it's a little bit easier. Now, when you're in the air, one of the other things that the APU will do is you have your engines. Obviously, when the engines are on, the engines are providing all of your electrical power. We're going to talk about the electrical system here in just a minute, but the APU also acts just as well, it's called an auxiliary power unit, okay? And the reason for that, it's kind of your auxiliary, it's your primary backup source of power. So if you have an engine go out, then you would be down. So you remember how the other day we were talking about redundancy in aircrafts? It always has 2 or 3 or sometimes even more systems of each of the same thing, like in order to rely on each other. So if you look at an aircraft always needing 2 of every system, so when an aircraft is functioning under normal power, like under normal conditions, it has 2 electrical generators. One comes from each engine. Okay, so the APU doesn't, as long as both engines are running, then as long as I should even further say that as long as the generator portion of each engine is running, then the APU doesn't need to be on at all during flight. Now, if you were to have one of your engine generators, we're going to talk about these in a minute, so you'll learn more about that, but each engine has an electrical generator on it as well, just like the APU does. If one of those engine generators were to go out, then the primary backup is going to be the APU. So if an engine generator goes out while it's flying, then the crew will turn on the APU and run that as an additional generator. They always have to have 2 generators at all times providing electrical power. And that's obviously just for the redundancy factor. So there's an MEL, same thing. We'll look at MELs later too, but there's an MEL called an IDG MEL. IDG MELs that stands for the Integrated Drive Generator, and that's basically your engine electrical generator. So you don't need to write that down right now, but we'll look at it later. But that's the engine generator. The APU serves as the auxiliary backup electrical generator when the engines are on. It's the primary generator when the engines are off on the ground, but in the air it's the backup. It's the first auxiliary backup generator. So in an airplane, in order to lose all of your electrical power in an airplane, not only do you have to have both of the engine generators go out, you'd also have to have the APU go out. So, I mean, in order for stuff to happen to airplanes, it takes, all of these systems are completely closed off from each other too. They are completely self-contained. The fact that the right engine generator goes out would have absolutely no connection to why the left generator would go out, if that makes sense. Now, you might have a situation which is just causing everything, if you're flying through volcanic ash, it's going to just be affecting all engines. But aside from that, if it was an internal problem in the plane and this one went out and then this one went out, those problems aren't necessarily going to be related to each other at all. So, but in order to lose electrical power, you got to have both engine generators go out plus your APU, and then even if that happens, the last line of defense is they have this little thing. It's called an air-driven generator. Yeah, it's called an ADG. We do test flights a lot for ADG drops. You probably hear about them. It always usually requires a check airman, but an ADG is this little, it's like a fan that has these big steel fan blades on it, and it's directly underneath the cockpit. But in an absolute emergency situation where you don't have any electrical power at all, no engine generators, no APU generator working, they can pull this lever, and below the cockpit it drops down this fan that has these, and then it hits the air and then it makes it spin like a windmill, same idea as wind power, but it drops down and it's really loud. Some people call it a RAT, R-A-T. We call it an ADG. It just depends on the type of aircraft. But a RAT stands for Ram Air Turbine, and ADG is air-driven generator. I mean, it means the same thing, but you might hear other people refer to it as a RAT. But anyway, ADG, they hit the lever, pull the lever, it drops the ADG down, and then it, the fan blades come out, and then it just starts, grabs the air and starts spinning, and that windmill will just create that, wind power to power up essential items only. It's not going to necessarily light up the cabin, but it's going to provide electrical power to the systems that absolutely need electrical power in order for you to land, basically immediately. If you're in that situation, you're going to be landing immediately. So it
bigger than
depends on the aircraft, but
We had one on an American flight pop down one morning as they were doing their checks. I mean, if it pops open and you're standing right there, it'll knock you out.
yeah, it could kill you.
Oh, that's not big at all.
It's little, but it's heavy.
Yeah. Does it have the...
So you said that they accidentally deployed that?
Yeah, when they were checking the landing gear doors, that ended up popping down. So the door opens up, and then that pops down, and they have to ratchet it up and a whole bunch of stuff. And I was there sitting there holding it up while they're trying to get it back into place, and it's just like,
So that's what you need to know about the APU. I'm going to skip down to electrical here. Electrical key points. The aircraft uses both 115 volt AC and 28 volt DC power. The primary source of AC power on the aircraft is two engine-driven integrated drive generators, IDGs. That's what we were just talking about. So remember that, how it says that there. That's something you got to know as well. If I were to ask you, what is the primary source of power on the aircraft? Your response should be the engine-driven generators, or the IDGs. If I were to ask you, what is the auxiliary power, or what is the primary backup source of power, your answer should be the APU. If I were to ask you furthermore, what is your emergency source of power, that would be the ADG. So know your sources of power. What's the primary? What's the primary backup? What's the emergency?
and yeah, on this plane, the APU is out too.
Oh yeah?
Yeah.
What does the AG stand for again?
Air-driven generator. So this thing says the constant speed drives turn the IDGs at a constant RPM. So basically all that that's meaning is that, I mean, everybody knows that like the plane thrust will go up and down depending on if you're landing, taking off and stuff. So regardless of what RPM, you know, or what thrust setting the engine is at, the constant speed drive turns the generator at the same speed no matter what the power setting of the engine is, so that you're not getting these fluctuations in power, basically. So it, just like an alternator, in a car. So it works exactly the same way. In fact, an alternator is basically a constant speed drive. So this is going back. It says the APU provides an alternate source of AC electrical power. The ADG provides an emergency source of AC power. The ADG deploys automatically when both main buses are without power, and it may be deployed manually. So when it refers to the buses, it's talking about those are electrical buses. We don't necessarily need to we're not going to get too in-depth involved in looking at all the different buses on an aircraft, but basically what it means is they're a bus, like an electrical bus, like you have several, like within an electrical system you have several different what are called buses, right? I'm sure you've probably heard the term. I'm not sure if everyone understands what it is, and you don't necessarily need to understand too much other than just there's all these different buses that operate different parts of the electrical system. There's two buses which are called your essential AC buses. And the essential AC buses are the buses that provide electrical power to the essential items on the aircraft in order for it to operate. So the only reason I'm even mentioning that, you're not going to be asked anything about any sort of a bus or an essential bus, but the only reason I'm saying that is because what the ADG senses is it senses when those two main electrical buses, the essential AC buses in this case, when it senses that those are without power, the ADG will automatically deploy. So one of those engines, those engine-driven generators, the IDGs, powers up one of the buses. So there's a right essential AC bus and a left essential AC bus, and one comes from the right engine, one comes from the left engine. So if the left engine goes out, then they're going to see a thing that says, you know, left AC essential bus is not operating. They're going to get a warning for it. That's what would ultimately prompt them to turn on the APU. The APU can then light up that essential bus with the IDG not working. If the other IDG stops working, you know, it's going to turn off the other AC essential bus. And so that's basically where the ADG is sensing whether or not it needs to be deployed. And like I said, the crew can also deploy it manually if they think that they need to. But regarding the electrical system, the main key points that you guys need to know are just that the primary source of power are the two engine-driven generators, the IDGs. The backup source is the APU. The emergency source is the ADG. ADG power is distributed to the flaps, the slats, the pitch trim, the hydraulic 3B pump, and to the AC essential bus, which is what we were kind of just talking about. DC power provided by 4 transformer rectifier units, TRUs, two NiCad batteries store and provide a source of DC electrical power for normal and emergency operations. AC and DC power systems utilize power centers to manage and manage power distribution. The AC power center distributes AC electrical power to 4 AC buses. DC power center distributes DC electrical power to 9 DC buses. So that's not all. Most of that stuff is you don't have to worry too much about. Okay. The environmental control system. Environmental control system, referred to as the ECS, provides regulated, conditioned air to the flight deck and the passenger cabin. There are two air conditioning packs on the airplane. The left one supplies air to the flight deck, and the right one supplies air to the passenger cabin. Seems a little skewed, doesn't it? Now, with the AC packs, if one of them is out, the other one can actually do the work for the other one, although you're not going to get as good of quality performance, you know, as good of air conditioning, essentially, in this case. But it's kind of funny because a lot of times, so you notice how the left one provides, the left one supplies air to the flight deck and the right supplies to the passenger cabin. What's kind of funny is you will notice that when you see an MEL for a left AC pack in op, that one is very common for crews to refuse. If you see one for the right side, they really don't care.
Of course.
Now, like I said, either of these two packs will do the work for the other one. So even if the right one is out, the left one can still provide air. Obviously, it still has to provide air to the flight deck, right? And vice versa. However, it's just if the right one is out and then if the left one is out and then they're relying on the right one, it's going to power up, or not power up, the best air that it's going to provide is the air to where it normally is supposed to. And then if it's having to take over the duties for the left pack, it's kind of like it will send the air that way and the air will reach there, but it's just not as powerful. Like if you were to flip-flop it and the right one, the left one was working without the right one, the flight deck would still feel normal, and the passengers would still get air, but it would feel less than as if, you know, the left one was out. So anyway, it's kind of a funny thing to watch for. The forward and aft cargo bays are pressurized, which means you can put animals in them. If one of those, a lot of times there's a little fan in each of those cargo bays, and you'll see like an MEL for like cargo fans. As we go through these systems, I will talk a little bit about MELs, like key MELs in each of these systems, but do know that we will also be going back through MELs in its entirety. So I like to kind of start to mention them now, though, so that you can kind of, once we do hit them, you go, oh yeah, we talked about that a little bit, you know, kind of look back at. Anyway, you have cargo fan MEL, so there's a forward cargo fan, aft cargo fan. Anyway, so a lot of times it will, if you have one of these cargo fan MELs, the restriction on the aircraft will be that it'll say no animals. And so you also are supposed to relay that information. As a system controller, are supposed to relay the no animal MELs downline to the stations. Because if they don't, you know, now some of these stations can look up MELs, and even if somebody doesn't call them, they can still have ways of looking to see that it's a no animals aircraft. But you do get into situations where somebody didn't call and then somebody put an animal on one of these airplanes, and depending on the length of the flight and the altitude that it goes to, said animal may or may not live. Also, a lot of times too is you have, even if the fans were working, sometimes they fail in flight too, you know. So They can go out in flight, which unfortunately can make it so whatever animals may have been in there during flight, may or may not be living at the end of the flight. So very unfortunate for the pet world.
Just emotional support animal.
Right,
Check
yeah, there you
your
go.
dogs. It's that important you don't check your dog.
Send them in my car. Yeah.
Yeah.
I'm allergic and I hate it when I'm in my seat. So gross. But it's like 400-pound German Shepherd though.
The big German Shepherd.
The guy was in the back.
So this next one here, it says only the aft cargo bay is ventilated with air-conditioned air. So even though both cargo bays are pressurized, only the aft one has the air conditioning. So you could technically put animals in the forward, however, it might get really cold. Typically, they always will put, on the 700, you always put animals in the aft cargo bay. So. But then again, you hear about, little kids or, like 8-year-old kids or 9-year-olds, 11-year-old kids, whatever, that hide away or stow away like in the landing gear. And most of those, I've heard pretty crazy stories. Most of those, so those landing gear bays that they can go up into are, pressurized, but most of those aren't, they'll just become extremely cold in flight. They're pressurized, but not air conditioned or, heated.
Didn't it fly from like LA to Hawaii?
Yeah.
Something crazy.
And
He was a little disoriented, but he was there.
yeah, and that one was not air conditioned. Yeah. They said that the only reason they think that he survived was because the landing gear, and I don't even know what wheel it was or whatever, but as it was going down the runway, obviously those tires, as they're spinning and rolling down the runway carrying that load, will create, the aircraft tires become extremely hot when they're rolling, down a runway. So way hotter than like a vehicle. So they think that the heat from the landing gear, and in this case, obviously it was a bigger plane because it went to Hawaii, so it was probably one of the rear landing gears that has, 3 or 4 wheels, basically. All that heat coming off of those, and then him like stowing away next to that with that heat is probably what kept him warm enough, basically. It's the theory that why he lived. But a lot of times, too, he just happened to be in an airplane where that was even pressurized. In most cases, most aircraft, the landing gear bays are not pressurized. So, kind of a lucky situation overall. If it's not pressurized, obviously you're screwed. It doesn't matter. Once you start getting above 10,000, 11,000, you're going to start not being able to breathe very well, but especially once you get 18,000 feet and over, you're doomed pretty quick. So let's see, conditioned air from the packs is blended with filtered recirculated air to optimize ECS performance. So recirculated air. So everyone wants to know why people get sick on airplanes. It's because the air is filtered and recirculated. Except on the 200. So if you want to know the healthiest airplane to fly on that we have, it's the 200. The 200 does not recirculate air. It just is all pass-through air. So it's all new, nice, fresh air. Whereas if you're on the 7, the 9, and really any plane, and whether it's us or any other plane for like mainline airlines, all of the bigger planes, those are all recirculated. This next thing says that recirculated air can be up to 34% of the total airflow. So basically a third of the air that you breathe in an airplane is air that's just being recirculated around the airplane. People coughing, sneezing, farting.
I'll get gases.
Let's put that under your, in the recirculated.
She's more senior than me, that's fine.
Single pack operations, this is one you need to know and remember. Single pack operations are limited to flight level 310. So if one of the packs is out, my max altitude is going to be 310. And ultimately that will create other problems associated with having to fly lower. You fly lower, you burn more fuel. I mean, it's going to affect everything. It takes longer because the air, you know, when we learned about air density and air pressure, the higher you fly, the less dense the air, the faster you can go. If you have to go down to 310, that's going to be it's not like it's way dense air, but you have to fly at 310. It is going to burn more fuel than if you were flying at 37,000 feet. And it is going to take longer as well. So those things will affect performance. 2 dual channel system controllers monitor and control the air conditioning systems.
Yeah, I think a fire too.
Let's see here. See, when I did these PowerPoints, they were based on the order that I used to go in, but that's not necessarily the order that I go in anymore. Let's see here for a second.
Everybody know that?
I think it feels great.
Yeah, I'm pretty happy, I'm pretty content.
I'm glad
I
I
worked on Tuesday.
Yeah, I'm freezing. I can hold it.
Oh, the fan, you can't sit there, I have to move somewhere else to the fan.
It's like this.
But you know me, I'm always there.
Hmm?
You're never cold.
I know we don't have any cold people in that anymore. My normal is Wednesday, so there's never any heaters.
That's what I used to hate working in the road, because you'd always have that
I had to
heater.
dress different on my
I
legs.
know, and it's not like she would like dress down, she'd still have a coat and stuff, and then she'd have that
I'm excited for her to plug in her heater and knock out like 7 dispatch desks at once, so she's knocked out ours so many times.
Okay, we'll take a break again for a second here. We've got 2 last things to go over, flight controls and hydraulics, but we'll take a break first. So let's talk about flight controls real quick. We'll hurry and get through these last 2. So flight controls. The wing is an advanced technology airfoil manufactured as a single unit and bolted to the fuselage at 10 separate locations. You got your primary flight control. So this is something you're going to need to know. If I ask you what are the primary flight controls, you would say elevators, rudder, ailerons, multifunction spoiler ons.
What was that last one? Ailerons and
Multifunction spoiler ons. Then we have secondary flight controls. Same thing. Be able to name these. Horizontal stabilizer trim. Slats and flaps. Multifunction spoilers. Ground spoilers. Aileron and rudder trim systems. In case any of you inquisitive crew support people would like to know what the difference between needing a check airman for a test flight.
Okay, wait, can you go back?
I will go back. I will. I will.
Wait, back into it.
I know. I will.
You go up on
Yep. So,
I'm like, I can't write quite that fast.
well, you can go back and look at this too. Like, you have access to this PowerPoint. Let's see.
Oh, thanks, Adam.
It's not one of those things that's going to disappear. If there's a problem with any of the primary flight controls, that will need a check airman on a test flight.
Okay.
Secondary doesn't. Anyway, there you go.
Thank you.
Everybody got them all? In an extreme emergency, primary flight controls remain hydraulically powered by the AC motor pump 3B. Power control units hydraulically move control surfaces from mechanical inputs of cockpit controls.
I hear PCU all the time too.
Yeah. Yeah, PCU, like they change out PCUs and stuff.
Yeah.
Yeah, anytime they have an issue with any of the flight control systems, one of the first things they look at is replacing the PCU. So sometimes those go bad because they basically will like it says here, it's the one that actually controls the hydraulics to all of those different flight controls, and it's based off of whatever the captain and first officer are, inputting in the cockpit. So it's like a computer, really, that says a power control unit, but it's really, a lot of times they'll call it a computer. It's reading and then, basically carrying out what it's being told to do. Multifunction spoiler ons operate on the downgoing wing only to assist the ailerons in roll control at lower speeds. So in case you're wondering what the multifunction spoiler on is, a lot of times if you spend much time looking at the wing when you're flying around, if you look out there, when a plane turns on the down wing, you'll see these little things like kind of pop up. They're like the spoilers, like when you land. Everybody I'm sure has seen the spoilers. As soon as like the wheels hit the ground, you have those things that flip up on the wing. Those are spoilers that help slow down. They kill the lift on the wing. So if everybody kind of remembers how the lift works, how the air is going over the top and then underneath, well, if you hit the ground and then you have a thing suddenly pop up, you can imagine the air coming over the top of the wing, hitting that, and then having to go up again. So it dramatically reduces the lift. So it helps, slow down the aircraft, keep it on the ground, basically. But the multifunction spoiler-ons, when the plane is turning, they're kind of like spoilers, except they're further out on the end of the wing, and they will kind of like gradually lift up to help the plane not like roll, so much, to keep the pitch angle kind of in check. That's all it's really doing. They don't really do much other than that. A rudder travel limiter is installed to prevent the pilot from overstressing the vertical stabilizer. The rudder travel limiter monitors flat position, airspeed, weight on wheels, and engine operation to limit the rudder travel. So if you're clear up in the air going fast, it's going to, the capability of the rudder is going to be limited as you slow down and are, you know, descending into an airport on approach, and you're going slower, well, the capability of the rudder to move from side to side is going to open up a lot more. Like when you're doing those crosswind landings and stuff, you have a lot more rudder capability when you're going slower than when you're going faster. The flap system consists of one pair of inboard and outboard flaps. Flap positions are 0 degrees for up, 8, 20, 30, and 45 degrees are the other ones. You use 8 and 20 for takeoff and 45 for landing. So remember those ones there, the 8 and 20 for takeoff and the 45 for landing. I know we've talked a little bit about flaps, but just to kind of recap a little bit, the flaps are on the ends of the wing, not the ends, but I should say the back side of the wing. And when they're extended, I'm sure everyone has seen them like extend down to the varying degrees that they have on here. Basically, all the flap is doing is it's just changing the shape of the wing to kind of be more, instead of having to go, you know, if you think about the air going over the top of the wing and then flowing off the back just straight, well, if the flaps go down, then that's making that air have to travel down further, and the air that goes underneath the wing then is kind of curving at the end and going underneath that flap. Basically, that whole process makes it so that the aircraft creates more lift. That's all it's doing. So when the flaps are up, the aircraft isn't creating as great of lift as when the flaps are down. So when you look at these different flap positions, it says here 8 and 20 are for takeoff. So you always will usually have, well, you do always have the flaps down to either 8 or 20 on takeoff. The difference between 8 and 20 is really going to depend on the outside conditions, the runway length, and things like that. If you have the flaps at 20 degrees, you're going to be able to take off sooner as you're rolling down the runway. The reason why, kind of the same thing, the higher the degree of flaps, the more lift the wing creates. So as the aircraft is going down the runway, it doesn't, if you have flaps at 20 degrees for takeoff, then the aircraft doesn't have to go as fast to take off. It can take off quicker because it doesn't need to gain as much speed because the flaps are creating more lift. However, the downside of having the flaps at 20 is that it decreases the overall performance. So it decreases your takeoff weight capability. So not necessarily, and in some cases it doesn't really make, you know, an actual effect, but in general, generally speaking, flaps 20 for takeoff will be worse takeoff weight penalty, even though it's allowing you to take off quicker. So the ideal situations of when you would use flaps 20 is if you were taking off on a relatively short runway. And, you know, the shorter the runway, the quicker you need to get off the ground, obviously. Just basic math on that, right? So on a shorter runway, typically you'll use flaps 20 so that you can get off the ground quicker. If you've got a nice big long runway, and you want to be able to take off like at a higher weight, flaps 8 is what you'll usually end up using. And that's just simply because the faster you're going, and with normal lift, it's going to help you take more weight. So so a lot of things kind of just depend on, you know, what the takeoff weight is, what the field length is, what the temperatures are. A lot of varying things are going to, you know, it's not like the dispatcher doesn't necessarily select 8 and 20. It usually is automatically selected. you can manually change it as the dispatcher to, if you wanted to just see differences and maybe see a different thing. But generally speaking, when you are doing a flight plan and you're doing your takeoff performance, your flap setting is usually automatically selected for you unless you manually go in and change it. Now for landing, as a plane is descending in, you'll see them initially, they'll go down to, you know, flaps 20, then flaps 30, and then eventually they'll go all the way down to flaps 45, and they land at flaps 45. So, but it's the same. It's the same principle, though. The flaps on landing is going to, especially when you talk about like flaps 45, as you're landing, it's just helping the plane go slower and still maintain lift. That's really all your flaps are doing. If you didn't have flaps down at all when you landed, then you'd have to land at a really fast speed. Like you'd have to land at, you know, 200 plus miles an hour probably. But when you crank down the flaps, the plane, once again, it's creating more lift because of the flap angle, and then it allows the plane to go slower and still keep itself in the air. So
When you use the 30.
the 30 is used just before, it's kind of used on just the segment right before your final. It's gosh, they probably only use it for maybe, I don't know, maybe 30 or 40 seconds, because they'll go to flaps 20. As you start to descend, you know, as you're getting close to the airport, you'll go, okay, flaps 20, they'll leave it there for a minute or two, and then flaps 30, and they'll leave it there for a minute or two, and then eventually all the way down. And I'm sure you've seen it, because you see it go down, and then a few minutes later you see it go down some more, and then ultimately you see it go down all the way. And when they do go down all the way, it's usually a combination of several things. The gear will go down. As soon as the gear goes down, the next thing is the flaps will go to 45. So as soon as you hear the chime and then you hear the gear drop out from underneath you, then the very next thing is flaps 45. Typically, they will not go to flaps 45 unless the gear is down. So they kind of correspond to each other. They can also put the gear down at flaps 30, but usually they're doing the gear down, flaps 45 kind of simultaneously. Anyway, so that's kind of the flap positions, but just remember 8 and 20 for takeoff and 45 for landing.
Now, are those settings for like all aircraft or specific to the 700?
This is specific to the 700. Like in the E-175, it calls them completely different. It's flaps 1, flaps 2, flaps 3. It doesn't even have the angle. Just flaps 1, 2, 3, 4, and 5. Leading edge slats are installed and consist of 3 panels on each wing. The inboard slat is the largest, outboard the smallest. When required, slats are anti-iced with engine bleed air. So slats are the opposite of flaps, okay? These are on the front of the wing, and you don't, first of all, the Crj700 does not have slats. So this isn't something you'd ever see on the 200, but I'm sure if you've flown around ever in the 700 or the 900, or really any like mainline aircraft, you'll notice that when they're using the flaps, that you'll see the front part of the wing will bow down and the back part of the wing will also bow down. And has anybody seen that or kind of noticed that? The 200, like I said, if you're flying a lot in the 200, you never see it because it doesn't have slats. You only see just the flaps, but in pretty much any other aircraft, they have slats on the front, which they basically do the same thing as the flaps do. The only difference is they're going front and they're going down. So ultimately, if you remember the normal shape of the wing, the flaps will go down and make the back part like elongated on the back and dip lower down. Well, the slats do the exact same thing on the front. They just push down like this. So ultimately, if your slats and your flaps are down, your wing looks more like an arch from front to back than it does like just the straight, you know. Just bring up the thing, but it'd probably take too long to go find a wing again. But anyway, the slat positions are 20 or 25 degrees depending on the flap setting. So when they put the flaps down, the slats are totally connected to the flaps. Like you can't independently put the slats down. When you put the flaps down, the slats are automatically tied to whatever flap setting you're doing. So it's all connected to the same little lever. So when they put the flaps down, the slats automatically go down. So but it basically just does the same thing. It has the same effect as the flaps. It's just helping create more lift, but for this one it's going to be on the front side of the wing instead of the back. Slats extend before the flaps, then retract after the flaps. Slats and flaps are both electrically operated. Inboard spoilers work with the multifunction spoilers in operation of the ground lift dumping system. So the ground lift dumping system is basically as soon as the wheels touch the ground, the aircraft can sense that, they call it weight on wheels, but the aircraft senses when there's weight being applied to the landing gear. So that's the way that the aircraft knows that it's on the ground. And then the aircraft in that same case knows to deploy the spoilers automatically and to, like with the slats and the flaps, like all of these systems ultimately are helping, you know, once you get onto the ground, they're all, once you get the spoilers up and your flaps are still down, all of these systems ultimately, once you're on the ground, help stop the plane as well.
And all of those are automatically deployed?
The spoilers are. Spoilers are automatically deployed. The flaps obviously have to be set as you're descending in, so they're already going to be down before you land, as well as the slats. The spoilers, all you do is you arm the spoilers. So they just hit this little button that it basically just arms the spoilers. Part of the landing checklist is arming the spoilers. And when you arm them, all it does is it turns on the sensor that as soon as the wheels hit the ground, the aircraft knows to deploy the spoilers. So they pop up automatically. If you can, I mean, when you consider like everything that it takes to stop an aircraft, I mean, there's a lot of interesting things. I mean, there's a lot of, you know, in a lot of cases, aircraft can just totally stop and slow down without using the brakes at all, depending on the length of the runway. But ultimately, you know, the idea is to get the aircraft to stop itself without having to use too much brake. That the brakes will heat up, you know, really hot, and like I said, the wheels are already really hot for, you know, being on the ground, spinning and carrying that weight of the plane. But when you think overall, kind of, I still can't really wrap my head around it, like the whole idea of lift and like weight, you know, like the weight of how, you know, of how it basically lifts an aircraft off the ground. But if you think about an aircraft, and what's really hard for dispatchers that don't have flying experience to kind of realize is you always want to like think about driving a car as similar to like driving an airplane down a runway. Now obviously flying is different, but if you think about an aircraft on the ground, in this case, like on the runway, it's like the only thing that I can compare it to obviously is driving a car. But the sciences behind like a car and a plane are like so different that it's like, you know, you think of like wheels and brakes and stuff, but when you think of like a car, like the way that it is, that it projects itself, or you know, the way it moves, obviously, is the wheels being powered, you know, turning on the ground, like, and you think about an airplane, which the actual, you know, airplane system, you know, with engines being up off the ground, not connected to the ground, you know, pushing or pulling the airplane down the runway. And then the wings, when they start to create lift, like when you're going a certain speed, you as you gain speed going down the runway, or if you're landing and you are reducing speed down the runway, like as long as you're moving forward, the wings are always going to be creating a certain amount of lift. So right when you touch down on the ground, even though there's weight on the wheels, it's usually not a lot of weight because the wings, even at that point, just due to the simple speed of the aircraft, are still supporting the majority of the weight. Even when the plane is completely wheels on the ground, like all three, your nose is down and everything, as long as the plane is still moving along, it's still supporting 3/4 of the weight of the plane. So you have to think of it like, even though all the wheels are on the ground, the wheels or the weight of the plane still is not fully on the ground. Like it's not fully on the ground until you are like down below like 70, 60 knots per hour. So if you're trying to like hit the brakes and stuff like at the higher speeds, it's almost useless because the plane, it's like the tires, if you think about it, don't have weight on them. So it's really braking the tires or even stopping the tires, it's really not going to do much because the weight of the plane is still mostly in the air. So it's kind of like I said, it's hard for me to wrap my head around it because you have to look at like everything totally different. It's the same concept when you look at like landing on an icy runway or a slippery surface. Like airplanes can do that a lot easier than cars can, and it's just simply because of lift. Like for an airplane going down a runway, like a car is going to slip and slide mostly because the wheels are connected to the ground, and that's your forward projected motion, right? So it's trying to grab the ground in order to move you. But a plane, if it lands on ice, that ice really doesn't have any bearing on the plane going a certain direction. It's not going to slide on ice because the weight of the plane is mostly still in the air, and it's going to go whatever direction the engines are pointed because it's using the air, not necessarily the ground. So you see a lot of situations where if you take a look at a runway and it's totally covered with snow, or I could probably bring up several videos of this type of stuff, but we can land on completely snow compacted runways. And if just like thinking about that from like my perspective, it just doesn't seem like it would ever work, because you imagine like driving a car down a snow compacted runway, hitting the brakes, sliding around, or even just as you're driving, you don't even dare to go fast because you're afraid you're going to veer off. And yeah, it's because you're connected to the ground, but a plane can land without sliding or any of those things just simply because the engines are up above the ground and that the wings are supporting the plane, weight-wise. So it's not affected by whatever your tires are rolling over at all. It doesn't have anything to do with it. You could land on dirt, you could land wherever you wanted. As long as it is a straight, long enough piece of ground, it's not going to really matter what it is you're landing on. So when you start looking at contaminated runways and things like that, the only time a contaminated runway really has an effect on an airplane is when it's going, less than, say 60 knots per hour, or when it's trying to, at the end, then turn off of a runway. Even slowing down, like you can think about it this way too, like the biggest thing that like people will try to relate it to is if you have an icy runway and you think about a plane, it's trying to slow down, trying to, completely stop. And if you think of it like an ice-covered runway or a snow-compacted covered runway, and then you think about like hitting the brakes, obviously in a car, you're going to slide. But in an airplane, they don't ever relate like the thrust reversers. Like they look at it the same way, I guess, as brakes, but it's like completely the opposite of braking because it's pushing the air. It's not trying to use the ground to stop. So I don't know if anyone's ever kind of thought about that or looked at it that way, but it makes situations where you would think that we would slide off the end of a runway because it's all iced up like it makes it totally safe, because the ice, isn't what stops it, or the ground isn't what stops the plane. It's the air that stops the plane. So as soon as those spoilers come up, it's trying to dump all of the weight onto the wheels. The only way it dumps all of the weight of the plane onto the wheels is by getting to a slow enough speed to where the wings aren't creating any lift at all. And that's when the weight is on the wheels. But even when the weight is 100% on the ground, the driving force of the plane is still the engines. Even at that point, it's not like the tires don't, you can't hit the gas and spin the tires, right? So the tires are not going to be the driving force still. So even if you're driving over ice or taxiing over snow and stuff, you're never going to spin or slide or spin out. You can slide if you use the actual brakes, you can slide, but like stopping the plane and propelling the plane aren't going to ever be, nothing's ever going to come into play with the, with the snow and whatever condition the ground is on. So, let me get into hydraulics real quick here. Okay, hydraulics. 700 is equipped with 3 independent systems. Each of those systems has 2 hydraulic pumps. So we have 3 hydraulic systems, and each hydraulic system has 2 hydraulic pumps. The main pumps, referred to as A, supply normal system pressure. Pumps 1A and 2A are engine driven. And then 3A is an electric pump. So out of the 3 systems, System 1 and System 2 are going to be the engine driven hydraulic pumps or hydraulic systems. And then 3A is an electric pump system. And then backup pumps, B, supply supplementary pressure during takeoff, landing, or when manually selected by the pilot. Pumps 1B, 2B, and 3B are all electric. So, kind of going back to looking at the way this works a little bit more in depth there. So when you look at systems 1 and 2, so once again you have 3 systems, each one has 2 pumps. So you have System 1, System 2, System 3. So System 1 has 2 pumps, which are called 1A and 1B. And then same with System 2 has pump 2A and 2B, and then System 3 has 3A and 3B. So if you had an engine failure on your left engine, then that is going to shut down hydraulic system 1. So this is kind of going back to the redundancy thing again here. System 2 is running from the right engine, and as long as that engine is working, that system is working. But if that engine were to fail as well, then System 2 would go down. Now, when you say System 2 would go down, it just means that the pumps 1A and 2A go down, basically, is what that means, because those are engine-driven pumps. So the engine has to be working in order for those pumps to be working. So
if 1A and 2A go down, would it just end up being 1B and 2B that kick on?
yeah. Now, if 1A and 2A go down, then you're probably, in a whole lot of more trouble than just the hydraulics going out. Because in order for 1A and 2A to go out, you actually have to have, the engines go out. So now, with that said, though, those things supply, hydraulic pressure to a lot of different areas of the plane. But if 1A goes down, then 1B can pick it, can still make those work. So it's basically saying that if you had your engine go out on engine 1 goes out, which causes pump 1A to go out, you can still make whatever that pump hydraulic, whatever it's basically, what's the word I'm looking for? Whatever hydraulics are connected to pump 1A are also connected to 1B. So even without the engine working, you can still turn on 1B pump and make all of those things work, even though that engine isn't working. The engine can be out, but like let's say engine 1, makes, is tied to the aileron and the spoilers and stuff like that on that left wing. So without that 1A pump working, then the aileron on that side wouldn't work. But then you can turn on pump 1B, which is electric, and it would send hydraulics still to the aileron. So you could still, even though that engine is not working, you could still have control over the aileron and the spoilers and stuff like that for that engine, or the landing gear. I mean, there's a lot of things that are connected to. So, and then, in a worst case scenario, you have your complete backup system, which is system 3, and it has both A and B pumps are electric. But any of these systems can make all of the other systems work though too. So they're all interconnected, and the whole thing can run off of system 1, the whole thing can run just off system 2 or system 3. So there's really 3 levels of redundancy on this one. Sometimes you'll see that we have, now sometimes even without engine failure, the pump itself just doesn't work, So in order to have the pump work, the engine does have to be on. But even with the engine on, sometimes the pump still can go out, just like any other pump, right? So sometimes you'll see an MEL for hydraulic system pump 2A, or you'll see one for system 3, like a 3A pump MEL, a 3B pump MEL, and depending on what systems those are operating, hydraulically operating, you might see limitations on those particular things. Like, like system 3B as an example, I believe helps the landing gear go up and down. And so without 3B operating, that means that the other systems are going to have to kick in and send its hydraulic fluid now to what 3B normally is, operating. So with 3B out, sometimes it takes the landing gear longer to come up. Like it takes like 10 to 15 seconds longer than it would as if it was normally running on 3B. And that's just simply taking longer because it's having to use the resources of the other pumps to get the hydraulic fluid and to get them up. So you'll see like little limitations like that. And we'll look more at those specific limitations later, but just to kind of give you an idea of when any of the pumps is having to do the work of another pump that might be inoperative, it's going to take longer for whatever that system was doing. It's going to take it longer to like respond or operate is all it's really kind of saying. But all 3 of these systems can operate any of the others, so they're all connected to each other and all redundant. Systems 1 and 2 are similar in operation except for reservoir capacities. So hydraulic system 1 powers the rudder and elevators. So remember these ones here. Hydraulic system 1 powers up the rudder and elevators, the left aileron, the outboard multifunction spoiler panels, the outboard ground spoilers, and the left thrust reverser. So when you go back and talk about the pumps, like I said, there are 3 systems here. Each of them have 2 pumps. So there's 6 hydraulic pumps total, but the ultimate thing here is that we have 3 hydraulic systems, and in order to fly, you need 2 of them operating at all times. So a lot of these aircraft systems that we go over, you'll see that there's, we have 3 of a lot of stuff, and that's really just to allow us to still be able to fly if one of them goes out. We have a backup. Now, if 2 of them go out and you're down to 1, you can never fly an airplane with having just 1 of anything, pretty much. Whether that be engine, whether that be hydraulic systems. The only thing that really is applicable to that would maybe just be the air conditioning packs. You can fly with 1 pack, but hydraulic system 2 powers the rudder and elevators. Also, the right aileron, inboard multifunction spoiler panels, the landing gear alternate extension, the right thrust reverser, and the outboard brakes. Systems 1 and 2 are cooled with a heat exchanger. Everybody good on that slide? Okay. Good. System 3 uses 2 electric pumps. Hydraulic system 3 powers rudder and elevators. So you notice if you take a look at system 3, it does almost everything. It's like the ultimate backup. Rudder and elevators, left and right aileron, inboard ground spoilers, landing gear, nose wheel steering, inboard brakes. Everybody good?
That nose wheel steering is just a little wheel that's behind the pilots.
System 3 has no special provision for cooling. Emergency electrical power, the ADG that we talked about earlier, is provided directly to pump 3B to maintain hydraulic pressure to the flight controls during loss of AC and engine power during flight. So going back, we talked about that when the ADG is dropped, we were talking about how it only powers up certain things. Well, hydraulically speaking, the only thing that the ADG lights up is going to be hydraulic pump 3B. And the reason there is because 3B pump is tied in to the essential flight controls. So like I said, if you're running on ADG power, you're not going to necessarily see full electrical power. It's only going to operate some things, and one of those things, the only hydraulic pump that it even turns on is 3B, and that's because 3B is connected to all of the essential things that you need to actually fly and land the plane. Cool. That's it with hydraulics. Any questions on anything? Okay, I think we have covered everything we need to cover today. Stuff you'll see on Monday will be more into the ice and rain protection, the avionics, communication, and navigation. We already talked about the power plants and auxiliary power units today, so that won't be, that's already been covered. Then emergency and abnormal procedures, fuel systems, and sources. So yeah, if you guys don't have any questions, then we are good for today then.